Hovering charge. A small charged pith ball, that's up here, with mass 4.2 times 10 to the minus fourth kilograms, hovers in place 3.8 centimeters above an insulated sphere with a positive charge of 0.25 microcoulombs. Draw a free body diagram showing all the forces acting on the pith ball there. What is the sign of the net charge of the pith ball? Determine the magnitude of the electric charge on the pith ball. If we have the charge on a pith ball, determine the magnitude and direction of its initial acceleration. Since the pith ball has mass, we can draw its weight vector, mg, downward, right? Gravity's always down. The pith ball hovers in place, so there has to be a force holding it up. This is the electric force, and it points upward. Since it's not moving, it's hovering, the acceleration is 0, just sitting there in place, in the air. What is the sign of the net charge on the pith ball? Well, since the electric force on the pith ball is upwards away from the sphere, the pith ball is being repelled from the sphere. We know that like charges repel, so the pith ball must be charged the same as the sphere. Now, since the sphere is positive, the pith ball also has to be positive. Determine the magnitude of the electric charge on the pith ball. And here's our handy givens up here. We put them in one place to keep track of them. And what do we have? Here's our Newton's second law. The sum of the forces equals ma. The upward force is the electric force, so that's positive. mg is down, that's negative, and that equals ma. But we already said a is 0 because it's not moving, so the electric force has to equal mg. So now come on up here. And what is the electric force? Well, it's Coulomb's law, kq1 q2 over r squared equals mg. All right, here's Coulomb's law. We're trying to solve for q2. q1 is going to be the charge on the sphere. So we kind of skipped a few steps here, but that's okay. If we want to get q2 by itself, we have to multiply by r squared, right, because it's in the denominator, so there it is on the right side. And of course, anything we do to the left, have to do to the right. Then we have to divide through by kq1, right, this term here, and there it is. And we have mg on the right side. So q2 is mgr squared divided by kq1. And let's just erase all this now that I pointed it out. Now we just plug in numbers right here. Okay, we have the mass of the pith ball, the acceleration due to gravity. We have the distance between the top of the sphere and the pith ball, and make sure you square that. Here's our constant k, and here's q1. We were given that. Now, what were the pitfalls here? Right here. Make sure you convert centimeters to meters by moving the decimal point 2 to the left, and convert microcoulombs to coulombs by multiplying it by 10 to the minus sixth. So when you do all that, the charge on a pith ball is 2.62 times 10 to the minus ninth coulombs. Now, what is 10 to the minus ninth coulombs? We call that nanocoulombs. See, nano, 9, sounds kind of the same. So the pith ball's charge is 2.62 times 10 to the minus ninth coulombs, or 2.62 nanocoulombs. Okay, we now have the charge on a pith ball. Determine the magnitude and direction of its initial acceleration. So q2 new is going to be 1.31 nanocoulombs. That is half of the value that we solved for in part C, right? Because that was 2.62, so we cut it in half. Now, if we reduce the charge on a pith ball, we reduce the electric force as well. Well, why is that? The electric force, put an E here, is K Q1 Q2 over R squared. So if I cut this guy in half, the electric force will be cut in half. So you can see on the free body diagram, the electric force vector is half, and it's smaller than mg now. So which way is this thing going to accelerate? Well, downward, right? Because there's more force down than up. So we show acceleration down. Sum of the forces is ma. So we're going to go Fe. It's still pointing in the up direction. Gravity is down, so that's negative. And the acceleration is down, so we put a negative there also. Now here's where it's important to understand the physics and the equations you're working with. We don't want to do Coulomb's law again and calculate kqq over r squared. So we're going to solve Newton's second law for the acceleration and take a shortcut so we can avoid Coulomb's law. Well, we had this on the previous slide, and we had this on the previous slide. Okay? Now we halved the charge. That means that the electric force is halved as well, because Q and the electric force are directly proportional. Originally, the electric force was equal to mg, right? Because it was hovering, it wasn't moving. But the electric force is now half of the original electric force, so what is it equal to? Half of mg. So look what we put in for the electric force. 1/2 mg, then minus gravity's force here equals minus ma. Isn't this a lot easier? We subtract, we get minus 1/2 mg is minus ma, and we find that the acceleration is 1/2 g. And we've got it pointing in the down direction, so that's pretty good. And what do we have? What is 1/2 g? Well, it's half of 4.9, so half of 9.8, so it's 4.9 meters per second squared in the down direction.